Welcome to the Co-17B Canvas page here. You can read through this. I've got a little bit about myself. A couple things that I wanted to point out. First of all, grading for co-class. So this class is graded pass, no pass. And the way that I split my points out, 60% of your points are just coming from participation. So if you're attending co-class regularly, that's all you have to do. You don't have to do something extra to get those weekly participation points. If you're not able to attend live, then other options in terms of kind of meeting that participation requirement could be coming to office hours or watching the recordings of the sessions. So that's 60% of the points, and you just have to get 70% to pass. So there's kind of three other categories of things that hopefully none of them feel super high stakes. So one, I will have a weekly reflection assignment each week. It's just like 2 or 3 questions. One of them is always the same. The last question is always, what grade would you give yourself in Math 17B this week? And the 2 other questions are usually something so that I can try to get to know you a little bit better. There will also be weekly quizzes. So this week's quiz is the Tell Sarah More About Yourself quiz. But in general, the weekly quizzes will be something math related. And the idea is that you're going to get the points just for putting in the effort and turning it in on time. I'll give you full credit, but I will also actually grade it so that you can have feedback around what your written responses to math questions look like. And then the last piece of this I'm calling exam reviews. So you will have 3 short exams, not for me, but you'll have 3 short exams for your 17B class plus a final. And so 2 days before that, 2 days before each of those assessments that you have in Tutoring's class, I'm going to have an exam review assignment. It's not supposed to be extra work. It should be things you're already doing to get ready to study for those assessments. So a question came up in the chat around the weekly quizzes. So the weekly quizzes, the grade that you'll get in terms of like co-class grade is just based on completion. But I also want to give you feedback about the math. So you'll also see like a written grade from me. I'll have a rubric. And so you'll get feedback on like how you actually did with the math part of it too. But in terms of the co-class grade, completion is all you have to do. And I'm going to have you either do like take a picture and upload a picture or scan to PDF, or if you like to use a tablet to write on your tablet, that's fine. You can also upload that as a PDF. But we'll do all of that in Canvas for the co-class. A couple other things that I wanted to just point out about Canvas. And I know there's another question in the chat. I'll get to it momentarily. So another thing that I wanted to point out about Canvas, and I have joined, oh man, what's it? Sorry, I was new to this thing. What's it called? Campus Wire. Sorry, it's my first quarter with Campus Wire. So I joined the Campus Wire for the 17B class. And so it could be that that's really all you need in terms of getting the opportunity to have discussion and get help from peers. But I also do have a discussion set up in our co-class Canvas page. And this is a great place if there's something specific that you want to make sure that I'm covering in co-class. If you put it into that week's discussion, I'll be sure to see that before co-class. And that kind of goes back to a question that's in the chat right now in terms of getting help on discussion sheets or like homework questions. Absolutely, you can totally ask me for help on that. And we'll see whether we have time to get to those kinds of questions. Generally in co-class, office hours might be a better spot for that. But we'll just kind of have to see as on any given day how much extra time we have for that. But for sure, if you have those specific questions and you throw them in the discussion in our Canvas page, I will do my best to get to those in the co-class. I think that's kind of it in terms of me showing you around Canvas. If anybody's like confused about how to navigate Canvas at any time, for sure, let me know. So I will stop sharing that. A couple other things just in terms of my department. So the academic assistants and tutoring centers, we also, in addition to specialists like myself, have a team of fabulous undergraduate tutors. They've taken all these courses, they did well in these courses, and you have a couple of ways that you can work with our tutors. You can make individual appointments, and those appointments happen through the same like OASIS system that you would make an advising appointment. Or we also have drop-in tutoring for math, but that won't start until next week. Just a couple of things about notation. So if I've called this f of x and I'm asking for f prime, then I'm asking you to give me the derivative, not the antiderivative. We'll get there in a second. So in terms of derivatives, all those trig derivatives that you had last quarter, we need them this quarter, and you're going to need them for 17C if you're taking 17C. So the derivative of sine is cosine. So if I take this derivative, I'm going to end up with cosine of 3x. And then we have to remember that pesky little chain rule thing. And that is because I have a 3x inside, I need to remember to multiply by 3. It doesn't matter if I write the times 3 at the back or at the front. I'd say it's more common to put the 3 up front, but it doesn't matter where you put it. Now here, I try to, again, keep things pretty simple. This guy's a polynomial. We've done a lot of these. I bring the power down, multiply by the coefficient, subtract 1 from the exponent. So this is going to look like technically 10 times x raised to the first power, but we don't usually write the 1. Now e to the 4x, anytime I have an exponential, when we take the derivative of an exponential, we get the same thing back again. But we have to remember, again, with the chain rule, that exponent of 4x, I'm going to think about multiplying by the derivative of 4x, which is 4. Doesn't matter if you put the times 4 in the back or the 4 in the front. Convention usually puts the number out in front. And then if I take the derivative of negative 12, well, I get 0. We don't really have to write anything, but I'll put the 0 there just for completeness. Hopefully that went easily and people are feeling okay with this derivative stuff. We're just kind of jogging that math brain back into function again. I'm going to squeeze one more up here because in addition to exponentials and trig functions, there's another kind of function that we see a lot in the 17 series, and that's logs. So here is my third one here. And if my function looked like natural log of, I'll keep it pretty simple for now. So let's say that I just said natural log of, how about x cubed? Then when I take the derivative, our rule for natural log is that whatever was inside, if I've got natural log of something, my derivative looks like 1 over that something times, again, I need that chain rule piece, the derivative of the something. And the derivative of x cubed is going to be 3x squared. Now, someone more clever than I am might notice that actually, if this is natural log of x cubed, before I even take a derivative, I have the option to use log rules instead. And one of those log rules says that if I have an exponent inside of a log, I can pop it down out in front. So I'm not taking a derivative here, I'm just using a logarithm rule, which says that would become 3 times natural log of x. Now I can take the derivative. And now I'm going to get 3 times the derivative of natural log, which is 1 over x. And if you're worried that these two things aren't the same, they secretly are, because I've got that x squared that's on the numerator and the x cubed in the denominator. So two of those x's are going to cancel out, leaving me just that x in the denominator. So in terms of derivatives, when we've got logs in the mix, we have the option of either doing some work up front with the log rules or just diving straight into the derivative. We're going to be asked one of two things. Either I'm going to be told, here's what my derivative is. Remember, we have different notations for derivative. This is a pretty common one. Something like df dx, that's also really common. Y prime, dy dx, all of these are common ways to say we're looking at somebody's derivative. I'm going to stick with f prime of x for a second. So if I told you that the derivative for some function was 3x squared plus 10x to the fourth plus 5, and what I asked you for is the general antiderivative. And this question is saying, whose derivative is that thing we're looking at? It was an f prime, so if I'm taking the antiderivative, I'm looking for going back to that original function. And this thing happens to be a polynomial, which means we're just going to run that derivative rule for polynomials in reverse. So when we take derivatives of polynomials, we take the number up top, we multiply it down in front, and we subtract 1 from the exponent. Well, if I run that in reverse to find the antiderivative, I'm going to start by adding 1 to the exponent. So if I add 1 to the exponent here, I'd be at x cubed. And then personally, I just kind of think about this as, well, if this is a something x cubed, then when I take the derivative, 3 times what out in front would give me the 3 back. And that's a 1. The other way to think about this is to say, I'm going to start with the thing we have, the 3x squared, but I'm going to add 1 to the exponent and divide by the new exponent. And that's always going to work for polynomials. So anytime I am looking at a number times x, actually, let me put the n in the exponent, some number times x raised to the n, then to take the antiderivative, I'm going to take that thing, add 1 to the exponent, and divide by the new exponent. In section 4.6, there is this chart with antiderivative rules, and this is going to be one of the things on that chart. I'm going to pause for a second to say, there's a better chart in the book. It's just hiding in chapter 5. It's on page, see if I got it right. Yes, it's on page 345. I have the digital version of the book. I assume it's the same in the paper copy of the book if anyone has like the actual physical book. But I recommend basically memorizing what is on page 345 in that table. And I've actually added to Canvas some notes because I think it's worth memorizing some of the things in that table in an even more generic way. Okay, back to this problem. So my 3's are going to cancel out. And as you get faster with finding the antiderivatives, sometimes this is math that you're going to do in your head and never even write down. So if I think about this next one, that 10x to the fourth, I know I'm going to add 1 to the exponent, so I'll have x to the 5th. And then I'm going to end up dividing by the new exponent, but 10 divided by 5 is going to give me 2. Now for this last part, the 5 hanging off of the back, it's kind of funny, but I think for both derivatives and integrals, sometimes the more simple the piece we're looking at, actually the harder it is conceptually. But for the 5, this idea of I'm going to add 1 to the exponent and divide by the new exponent, it kind of works if we fake this and say sitting next to that 5 was an x to the 0 power. So when I add 1, that would be x to the 1st power. And when you divide by 1, you would just still have the 5. Personally, I think it's way easier to think, well, I have a constant. What kind of function has a derivative that's a constant? A linear thing. Now there's another piece to this because it said to find the general antiderivative. This is one particular function whose derivative is this thing up here. However, if I put a plus 467 hanging off the back of this, it has the same derivative. And if I made this plus 4.67 cubed, it still has the same derivative. Because this thing back here is just a constant. So to find the general antiderivative, we do the hard work, and then we don't lose points because we're going to remember to write plus c. I kind of put this in the same category as in 17A when you were doing limit problems, and some instructors are picky about making sure that you write LIM, like you have to keep writing limit on each line. This is another one of those things. So if we've been asked to find the general antiderivative, we want to make sure that we include that plus c. My function, so notation wise, this is telling me that t is my independent variable. It's the thing that's acting like x. So this time my derivative is going to be, how about e to the 5t plus 2t. And if I'm asked to find the general antiderivative, then again, I'm looking to answer the question, whose derivative is this? Notation-wise, because this says dy dt, I know that my answer is going to be a y equals, not an f equals. And this 2t part, this thing out here, well, that's a polynomial, so we can use that polynomial rule for antiderivatives. But this guy's an exponential. Just like he had his own rule for derivatives, exponentials, we got a rule for antiderivatives too. And here's the way that I think about it. Well, I'm just going to remind myself that if I had something like y equals e to the 7t, then when we take that derivative, we would get 7 times e to the 7t, because I've got that number that's multiplied by t up there in the exponent. Well, here, I don't want to end up with a number out in front, right? Because we took a derivative and we didn't end up with a number out in front. So the way that I'm going to kind of counteract that is I'm going to say, well, the function must have looked like e to the 5t divided by 5. You can always check your answer to an antiderivative by taking the derivative of it. And if I take the derivative of this and I go to find y prime, well, that division by 5, that's kind of the same thing as saying a 1/5. And then e to the 5t, when I take the derivative of that, I get e to the 5t times 5. and these 5s would cancel out. And I'd have exactly what we wanted. So it doesn't quite follow exactly the same rule as our polynomial thing, but it is true that because we were finding an antiderivative here, we kind of end up dividing by a number. When we were taking derivatives, we end up kind of multiplying by a number. When we take antiderivatives, we generally end up dividing by a number if we just have a constant times x or a constant times t somewhere in the problem. We're not quite done because we still have to deal with the 2t. This is a polynomial. So the invisible exponent is 1. If I add 1 to the exponent, I'll have 2. So I'll have a t squared, and then I'll have 2 divided by my new exponent of 2. If I want the general antiderivative, I'm going to add in a plus c. And like I said, we can always check our work by taking the derivative of the thing we just found. So we made sure already that our exponential piece matched. If I take the derivative of t squared, I get 2t. And when I take the derivative of a constant, I get 0. So we're good. So there's a question about what would that look like as a general rule for the antiderivative. So if my f prime looks something like, I'm going to write it as e to the kt, then my original function was 1 over k e to the kt. And this is one of those general antiderivative rules that is on page 345 of our textbook. What I think is totally bizarre is that page 345 of our textbook handles when we have a constant next to the t up here in the exponent for an exponential function, but they don't tell us that the same thing works when we're looking at trig functions. So I'm going to add to that list on 345. We also should have this kind of generic thing for trig. So if I'm looking at an f prime that is, let me go with cosine here. It is cosine of 5x. And I need to know who's the function whose derivative is cosine. Well, that first step is to say, well, the function whose derivative is cosine is sine. So I'm going to start with a sine of 5x. But I know that if I took the derivative of this, I'd end up multiplying by that 5. Since I'm taking the antiderivative, I'm going to divide by that 5. Or more generally, this one is on page 345. This one's not, but it really should be. If my function is cosine of ax, then the antiderivative is sine of ax over a. By the way, I've used slightly different notation on both of these, but on each of them, I forgot the plus c. Sorry about that. I just lost a point. Dang it. It's okay. Hopefully I'm making the mistakes so you don't have to. So I don't know why this one, I don't know why they don't do it generically for the trig functions, but they do it generically for the exponential. Seems kind of silly to me. We can also do the same for sine. So if my f prime of x here is, well, now I'm going to make it slightly more confusing, and I'm going to call this sine of x over 2. One of the things that I try to make a big deal about when I'm talking about derivatives is I swear not everybody, overgeneralization. Many people have a special part of their brain related to fractions. And when they see fractions, weird math comes out of their hand or their mouth. And I think it's just like people have a fraction brain that like turns other logic off somehow. So I just want to know, when I write x over 2, that is entirely the same as saying 1/2 of x. And if you totally hate fractions and you'd rather think in decimals, that is also the same as saying 0.5x. And no matter which one of those you want to play around with, they're all just, we can think of each of these as being a constant times x. I know this one feels like division. This one feels like we're going to have to do something fancy, but they're all equivalent. And each of these is some kind of number times x if we're thinking about it. So when we go to find that antiderivative, the first thing that I want to do is say, well, who's the function whose derivative is positive sine? And this one we need to be careful about. But the derivative, in order to get a derivative of positive sine, my function had to be negative cosine. Calculus can never change the argument of a trig function. Only trig identities can do that, which means I have to leave inside the 1/2 x we started with. But just like what happened with our exponential function, what happened with cosine, when we're finding that antiderivative, we're going to end up dividing by the 1/2, that constant that's sitting in front of the x, plus b. I remembered this time. Or most generically, if my f prime is sine of ax, then my antiderivative is negative cosine ax over a plus c. It is important to note that that thing, like these rules, only work if that thing is a constant, right? If this were like t squared times t, this is not how life works. But if it's a constant times t or a constant times x, then these generic antiderivative rules will work. So we have 5 minutes left. So I've got one more antiderivative problem that I want to address, and that is, so far, all of these problems, I was asking for us to find the general antiderivative, but sometimes we might be asked to find a specific antiderivative or a specific function. I can link those up. So let's get something like that rolling. So let's say that I told us that f prime of x is equal to, I'll try to keep it simple here. So let's say f prime of x is equal to 6x, 6x plus 12x cubed. And suppose that we know that f of 1 is equal to 8. And I want to find f of x. Well, for starters, if f prime is equal to 6x plus 12x cubed, then we ought to be able to find the antiderivative of that. So if you didn't already do it in your head or on your paper, get our generic antiderivative for f just based on this. And you can type it in the chat if you're able to type stuff in the chat. Okay, looks pretty good. So right now, I've got that 6x. So it's got an invisible exponent of 1. And if I add 1 to the exponent, that'll make that x squared. And then I'll take the 6 and divide by the new exponent and end up with a 3. Here, when I add 1 to the exponent, I'll have x to the 4th. And then out in front, I'm going to take the 12 and divide by the new exponent and also get 3. I think that's what people wrote. Yes, that's what people wrote. Sounds good. And then I know that generically, that would be like a plus c. So sometimes we call this the family of solutions, right? And if I were to graph this, I'm not going to, but x to the 4th kind of looks like a W. So essentially all of these solutions are kind of like W's, but they're shifted up or down based on that plus c. So if you can imagine, we'd have this whole set of graphs of W's that are shifted up and down by a plus c. And we're looking at the very specific one that goes through the point x equals 1, y equals 8. So we'd be finding which of these happens to fall exactly on that point. We could do that graphically. We're not going to do that graphically. We are going to come into this thing and say, if we plug in 1 for x, we have to get 8 for y. So I need 3 times 1 squared plus 3 times 1 to the 4th plus c, all of that to add up to 8. I'm looking at a 3 plus another 3. So that 8 would equal 6 plus c. And that constant will need to be 2. Which means that our specific function, f of x, that matches these criteria would be that f of x is equal to 3x squared plus 3x to the 4th plus 2. And this, we sometimes refer to as the specific or the particular solution.